All right, today we're going to talk about something you think you know, states of matter. But we're going way beyond the basics you learned in school. Forget just solid, liquid, and gas. We're diving into the strange, the hidden, and the downright bizarre states that actually power our modern world. You know, in school, they probably told you matter comes in three main flavors: solid, liquid, and gas, right? And hey, maybe if your teacher was really cool, they even mentioned plasma. But what if I told you that's not even scratching the surface? Is that really all there is? Because honestly, the most fascinating and the most important states of matter are the ones that don't play by the rules. They're the ones that exist in those strange, wonderful gaps in between. And they are literally all around you, running the world in ways you probably don't even realize. So let's start with one that perfectly mashes up the properties of a solid and a liquid. It's this incredible intermediate phase that pretty much every single one of us interacts with every single day. Yep, that's right. The screen you are looking at this very second, whether it's on your phone, your laptop, your TV, it's all possible because of this weird in-between state. We are talking about liquid crystals. And the crazy thing is, this whole story started completely by accident, way back in 1888. A botanist, Frederick Reinitzer, was studying a chemical he got from carrots, of all things, and he saw something odd. He heats it up to 145 degrees Celsius, and it melts from a solid into this weird, cloudy, milky liquid. But it wasn't done. He had to keep cranking up the heat all the way to 179 degrees before it finally, suddenly, turned clear. It had two melting points. How is that possible? Well, that strange, cloudy phase in the middle, that was humanity's first look at a liquid crystal. So what makes them so special? It's a property called anisotropy. Now that's a bit of a sciencey word, but all it really means is that its properties change depending on how you look at it. The best analogy? Think of a pile of logs. All the logs are pointing in the same direction. That's order. But you can still slide them around. That's fluidity. This unique structure is the secret sauce for how they can bend and control light. This in-between thing is really the whole game. A normal crystal, like a diamond, it's super ordered, but it can't flow. A normal liquid, like water, it flows all over the place, but its molecules are a chaotic mess. A liquid crystal gets the absolute best of both worlds. It has enough order to control light, but it can still flow like a liquid. And this unique combo is exactly why they're so incredibly useful. I mean, we use them in all our displays, obviously, but they're also in temperature sensors that change color with heat. In medicine, doctors can literally paint them on skin to find veins or even tumors, which are just a little warmer than healthy tissue. They can even spot overheating parts in a circuit board before they totally fail. Okay, so we've gone from a state that blends solid and liquid to one that seems to just break the laws of physics entirely. Zero. That's it. That's the amount of electrical resistance in a superconductor. What does that mean? It means if you get a current flowing in a loop of superconducting wire, it will just keep flowing forever with zero, and I mean absolutely zero, energy loss. Now, this was actually discovered way back in 1913, but there was a huge catch. It only worked at ridiculously cold temperatures, just 4 degrees above absolute zero. For decades, the holy grail for scientists was finding materials that could do this at warmer temperatures. Then, in the mid-80s, the field just exploded. First, a breakthrough above 30 Kelvin, and then the massive game changer in 1987, a compound that worked at 92 Kelvin. So why was 92 Kelvin such a monumental deal? I mean, it still sounds crazy cold, right? Well, it's because it's warmer than 77 Kelvin, and that is the magic number. That's the boiling point of liquid nitrogen. Suddenly, scientists could use cheap, abundant liquid nitrogen as a coolant instead of the incredibly expensive and difficult liquid helium they needed before. This one discovery dragged superconductivity from a lab curiosity into the real world. And once it became practical, the applications just took off. Those unbelievably powerful magnets inside every MRI machine, they're built with superconductors. They are our best bet for building a future electrical grid that doesn't waste energy. And they can enable mind-bogglingly fast switching in the next generation of computers. Okay, so we've seen the in-between states. Now let's take a quick little tour of the extremes. And we're going to start with the single most common state of matter in the entire known universe. Get this: solid, liquid, and gas. Everything we think of as normal matter adds up to less than 1% of the visible universe. Less than 1%.
So what's the other 99%? It's plasma.
So what is this stuff? People call plasma the fourth state of matter. The easiest way to think of it is a gas that's been superheated and zapped with so much energy that its atoms literally get torn apart, creating this soup of charged particles. All stars, including our sun, are made of plasma. On Earth, we see it in the wild as lightning or the incredible auroras. And, of course, we've learned to create it ourselves in neon signs, fluorescent lights, and for really high-tech stuff like sterilizing medical gear and etching the microchips that run our lives. And now for something that's just plain weird. If you take a substance, let's say carbon dioxide, and you heat it up and you squeeze it, really squeeze it past a certain point, it just stops being a liquid or a gas. It becomes something else entirely, a supercritical fluid. It's this wild state that has the density of a liquid, but it can flow through things like a gas. It turns out to be an amazing solvent, which we use for everything from decaffeinating your coffee to creating really advanced materials. Now, the states we've seen so far exist under specific conditions, right? Temperature, pressure, but what if we could go beyond that? What if we could design and build forms of matter, atom by atom, that nature never even thought of? For the longest time, we thought we knew carbon. It was either diamond, super hard and brilliant, or it was graphite, soft and dark. That was it. Then 1985 happened, and everything changed. A team of scientists discovered a brand new form of carbon, made of 60 atoms arranged in a perfect sphere, just like a tiny soccer ball. They named it Buckminster fullerene, and with that discovery, they blew the doors wide open to a whole new world of materials by design. This unlocked a whole family of designer carbon. You've got the fullerenes themselves, these little spherical cages that can trap other atoms inside them, perfect for things like targeted drug delivery. Then, if you take a flat sheet of carbon atoms and roll it up, you get a carbon nanotube, a material so ridiculously strong for its weight that people talk about using it to build an elevator to space. And that flat sheet, that's graphene. It's 1 atom thick, stronger than steel, and an incredible conductor of electricity. It's poised to totally revolutionize electronics. So we've seen matter that's superordered, matter that's in between, even matter we designed ourselves. But for our final stop, how about we look at a state whose defining feature is a complete and total lack of structure? This is what we call an amorphous solid. Unlike a crystal, its atoms are just a jumbled mess with no repeating pattern at all. The best way to picture it is a liquid that was frozen in its tracks so fast that its atoms didn't have time to line up properly. And you see this stuff everywhere. Glass, plastic, rubber, they're all amorphous solids. So from the screen you're watching this on, to the stars lighting up the night sky, to materials that are still being dreamed up in labs, our whole picture of matter has just completely exploded. We went from 3 basic states to dozens of exotic and intermediate ones. And that really leaves us with one final big question. What's next? What new state of matter, with properties we can't even begin to imagine today, is out there waiting for us to discover or to design?